Hello, my name is Jack from Seoul National University. I'm glad to introduce our paper, which has been published in CVPR 2024. The title of our paper is Beyond Imageable Resolution for Image Recognition with Task-Driven Perceptual Loss. In real-world scenarios, image recognition tasks may encounter input images containing low-resolution contents, and this causes significant degradation in the task performance. Imageable resolution, or SR in short, is a promising solution to tackle this problem. However, we found that conventional pixel error-based SR methods are ineffective in boosting task performance, which dilutes the advantage of utilizing the SR method. So in this paper, our goal is to develop a novel task-aware SR framework, which we named SR for IR, where SR images can effectively benefit subsequent image recognition tasks. We start the problem with the question, why the conventional pixel error-based method is not effective. To benefit image recognition tasks, the SR should restore task-relevant details. However, pixel error-based method is not optimized from this perspective. To this end, we focus on the concept of perceptual loss, which is well known for effectively managing the high-level visual space. Perceptual loss is a technique in neural networks that minimize the difference between high-level features extracted from SR and HR images conventionally with pre-trained BGG network trained on the ImageNet dataset. Still, using the conventional perceptual loss does not guarantee the reconstruction of useful features for a specific task. To ensure the restoration of task-relevant details, we propose a novel method that calculates the perceptual loss on the visual space of the task network, which we named TDP loss. Furthermore, we enhance the efficacy of the TDP loss by addressing the potential two problems by proposing a novel CQ mix and alternate training framework. This is the overview of our method, the SR4IR framework. Our method consists of two phases, and in phase 1, we train the SRMS network with the proposed TDP loss while freezing the feature extractor from the test network. And in phase 2, we train the test network with the augmented images from the proposed CQ mix while freezing the SR network. Our task-driven perceptual loss, TDP loss in short, guides the SR network to restore task-relevant high-frequency details. Specifically, we maximize the similarity between HR and SR images within the latent space of the feature extractor of the task network as following equation. So since the output of the task network are substantially relevant to the task, our TDP loss can effectively guide the SR network to restore task-relevant feature. Since the operation of TDP loss is based on the learned weight of the task networks, the effectiveness of the TDP loss is inherently related to the training procedure of the task network. Therefore, there can be potential problem in case if a task network learns a biased feature, then the TDP loss may struggle to guide SR images to restore other valuable details. For instance, consider the bird classification scenario. If a task network exclusively learns big pictures to classify bird species, then the TDP loss may struggle to effectively guide SR images to restore other key high-frequency contents, such as wings or feet. This limitation could hinder the overall task performance boosting that could be attained through the SR method. To address this issue, we propose a novel cross-quality patch mix, CQ mix in short, which augments on input images by randomly choosing either HR or SR patches for each grid region. By doing so, CQ mix creates an image in which high-frequency components are randomly erased at a patch level, which increases the task network to use diverse high-frequency contents as a glue, hence enhancing the efficacy of the TDP loss. We further propose another strategy to enhance the efficacy of the TDP loss called alternate training. To effectively utilize the TDP loss, the task network must be capable of extracting the task-relevant features from both SR and HR images. Following the conventional perceptual laws, we can just simply use pre-trained and fixed task network for calculating the TDP loss. However, a task network pre-trained solely on HR images cannot effectively process SR images, reducing the effectiveness of the TDP loss. Therefore, we propose an alternate training framework which trains SL and task network alternately, enabling the use of an on-training features extractor when calculating the TDP loss. Specifically, in the first phase, we train the SL network with the TDP loss using a feature extractor from the second phase. In the second phase, since SR images are used to train the task network, we can guarantee that our feature extractor can effectively extract task-relevant features from SR images. In summary, the objective of our SR4IR in each phase are defined as follows. We use three image recognition tasks in our experiment: semantic segmentation, object detection, and image classification. We use a representative dataset for each task. For all dataset, we apply bicubic downsampling with scale of 4 and 8. And when training both SR and task network, there is a set of available training scenarios which we denote as I-error to T, S to T, T to S, and S plus T, and we compare our SR4IR with all of these baselines. For details on each configuration, please refer to our main manuscript. These are quantitative results of three image recognition tasks, and compared to the all baselines, our SR4IR consistently achieved the best task performance thanks to the successful restoration of task-relevant feature of our method. This is our qualitative results, and in the first and second columns, a task network trained on low-resolution images or conventional pixel error-based SR images produces inaccurate task performance result. In contrast, the third column, which is result of our SR4IR, achieves much more accurate results by taking advantage of the restoration of task-relevant details. We conducted ablation studies on each component of our method, and we validated that each proposed component significantly contributed to the performance boosting of our method. Thank you very much for listening. Our code and pre-trained models are available at GitHub. If you have further questions or want to make a discussion, please visit our poster session. Thank you.